Okay, I'll be talking to you about relaxed locally correctable codes. This is joint work with Tom Gore and Ron Rothblum. So these are specifically a type of error correcting code. So in the setup for error correcting codes, we have some message M that we'd like to encode in such a way that even if we perturb the code word with a little bit of adversarial noise, we can still recover this message M. So we call an algorithm that takes this string W that's close to a code word and returns the underlying message M, a decoder. And similarly, we'll call an algorithm a corrector if it takes the string W and outputs the code word that this string is close to. And some relevant notation for us during the talk, the block length of a code is the length of the code words. The rate of a code is the length of a message over the length of the encoded message. And some notation, we'll use K to denote the message length throughout the talk. Okay, so this is all well and great if we have access to the whole string W. But in many modern applications, say with very large databases, having access to the entire string W may be very expensive or otherwise infeasible. So Katz and Trevisan asked, what can we do if we only have local access, if we have query access to this string W? What can we recover? So we'll call a local decoder an algorithm that takes an index I of the message and makes some number of queries Q to this string W and outputs with high probability the ith symbol of the message. And a code is locally decodable if for any index I and string W that's close to the code, there is a local decoder M that makes Q queries to W and outputs the ith symbol of the message with high probability. And this 0.1 on the right-hand side is just some arbitrary constant. It can be amplified. Okay. So analogous to locally decodable codes, we can define locally correctable codes in a very similar way. Now a local corrector will take an index I of the code word, make some queries to the string W, and output the ith symbol of the code word with high probability. Okay, and the code is locally correctable if we have a local corrector for it. So LDCs and LCCs have all sorts of applications throughout theoretical computer science, private information retrieval, data storage, hardness of approximation, you name it, there's probably an application. And so it's very natural to ask, what's the state of the art for these useful codes? So for LDCs, there have been a bunch of beautiful works in the last 15 years that have gotten the block length for constant query locally decodable codes to something slightly less than sub-exponential in the message length. And for locally correctable codes, the best block lengths we have are exponential in k to the epsilon, where k is the message length. So this is in the constant query regime. And you'll notice that despite the incredible usefulness of these codes and all the attention that's been paid to them, this is a really huge block length. And specifically, it's considerably more than polynomial in the message size. So a major open question in this area is, can we get constant query LCCs or LDCs with polynomial block length? Okay, so this is not the only regime that's studied. Many people have also studied this constant rate regime, where the block length is linear in the message length. And a very nice recent work of KMRS established that there are LDCs and LCCs in the constant rate regime with roughly 2 to the root log k queries. So this is considerably better than k queries or any polynomial in k queries, but it still falls very short of something like log k queries or polylog k queries. So it's a very natural question of, can we get a constant rate code that has fewer queries? So motivated by the usefulness of these codes, as well as the difficulty in getting more efficient constructions, Bensason et al. Defined this very natural relaxation for locally decodable codes. And their key idea was to allow the decoder to say, I don't know how to decode if it sees obvious errors. So here we have Snoopy. He makes some queries to this purported code word, and he's trying to figure out how to decode the ith symbol of the message, but he says, I can't figure it out. I'm not sure, but it's definitely because of some corruptions. So they defined relaxed locally decodable codes. A relaxed local decoder takes in an index I of the message, makes some queries to this string W, and outputs either the ith symbol of the message or bot, denoting I don't know. Okay. And a code is relaxed locally decodable if for any index I and a string W that's close to the code word, we have that the relaxed local decoder almost always outputs the ith symbol of the message or don't know. But there's a problem here with the definition as I've written it. The problem is that we haven't prohibited the relaxed local decoder from just always saying I don't know. Right? If it always says I don't know, clearly this condition is trivially satisfied. So they added a second condition, which says if I give this relaxed local decoder a true code word, totally uncorrupted, it should always be outputting the ith symbol of the message and never outputting bot. So with this relaxation, they construct constant query relaxed locally decodable codes with block length almost linear. So a huge improvement over the block length of normal locally decodable codes. So it's very natural to ask, can we extend this to local correction? And this is what we do in this work. So a relaxed local corrector takes in an index I of the code word and either outputs the ith symbol of the code word or bot. And we have the same sort of non-triviality condition, that if the relaxed local corrector M is given a true code word, it should always be outputting the ith symbol of the code word. So in this work, we construct relaxed locally correctable codes in the constant query regime as well as the constant rate regime. In the constant query regime, we construct them with polynomial block length. And in the constant rate regime, we construct them with quasi-polylogarithmic query complexity. So it's something more than polylogarithmic, but not too much more. So as a comparison to existing work on locally correctable codes, in the constant query regime, we saw that the best block length so far is exponential in k to the epsilon, and for the relaxed version, we can get block length poly k. Specifically, this is something like k to the 4, our poly k. And in the constant rate regime, KMRS gets query complexity roughly 2 to the square root log k, and we get this quasi-polylogarithmic query complexity. So note that both of these codes, we said they're constant rate. Actually, they can be rate arbitrarily close to 1. And sort of the similarities between these are not really a coincidence. Our construction is very heavily inspired by the recent work of KMRS on locally correctable codes and locally testable codes. So that's all I'm going to say about the constant rate construction. For the rest of the talk, I'd like to focus on the constant query construction of relaxed locally correctable codes. So we show that there exists a constant query relaxed locally correctable code with block length roughly k to the 4. And how are we going to do this? Well, we describe a transformation that starts with a relaxed locally correctable code that has very large query complexity and transforms it into one with smaller query complexity. So how can we possibly do this? Well, one idea is that rather than making all the queries that this core relaxed corrector wants to make, we're going to provide some extra proofs to help out our core corrector. And instead of making all the queries that it initially wanted to make, it'll make a few of those queries, and it'll additionally make some few queries to some auxiliary proof we provide to help it out. So those of you who are familiar with the idea of PCP composition may be reminded of this. And in fact, it's very much inspired by this, and we call this composing a relaxed locally correctable code with a PCP of proximity. So let's just quickly review what a PCP is. A probabilistically checkable proof is such that it helps Snoopy verify if X is in some language, while he just has to make a few queries to this proof. So it helps him probabilistically verify if X is in some language with just some queries to the proof pi, and a PCP of proximity is a special PCP where Snoopy doesn't even have to read the entire input. He just makes a few queries to this input X, a few queries to this proof pi, and probabilistically decides if X is in the language L or not. So we're going to use PCPs of proximity in our composition theorem. Let's see what it looks like. So here's Snoopy. He wants to correct some symbol at location I star that lies in the core relaxed locally correctable code, and he samples some randomness R star to help him out. So based on I star and R star, he makes all these queries to this string W, and we want to help him out, so we provide all these auxiliary proofs. And now, instead of making all those queries to this string W, he just makes some of those queries, and he makes some additional queries to this proof pi I star R star that was written specifically to help him out in verifying this set of queries. So by the magic of PCPs of proximity, we could show that this actually works to correct the symbol at I star. And it yields a relaxed, locally decodable code. In fact, in retrospect, it's very similar to the construction of Ben-Sasson et al. For these relaxed, locally decodable codes. Okay, but there's an issue if we're going to claim that this is a relaxed, locally correctable code. What's the issue? We've described how to correct these symbols in the core by adding all these proofs. But now we've added all these proofs, and that's our new code word. And I promised you that we could correct any symbol of the code word, so we need to be able to correct these proofs. So the main technical ideas of our work of this construction come in correcting the proof strings. So how are we going to do this? Let's say that Snoopy wants to correct an index J star that lies in some proof pi I star R star that he was using before. One idea is to require that the set of valid proof strings itself forms a locally correctable code. So what can Snoopy do now? He can just run the corrector for this locally correctable code on this purported proof string he was given. And since the set of valid proof strings is a locally correctable code, if there weren't too many corruptions in this proof, then this string is close to a code word, and he'll be able to correct at the index J star by running the local corrector for this code. So this works when the proof is not too corrupted. And now we need to ask ourselves, is this enough? Is it enough that we solve this problem when the proof is not too corrupted? And I claim the answer is no. Why not? Because we've appended many proof strings, right? We appended one for every index of the core and every setting of randomness that Snoopy could sample. So if there are many proof strings in a single code word, then a single proof string is extremely small compared to the size of the overall code word. So it's totally possible that the proof could be entirely corrupted. And what do we do now? If the proof's entirely corrupted, maybe it's now close to some totally different code word, and running the local corrector won't help recover this symbol at J star. Okay, so one idea might be to add even more proofs. If you add even more proofs, you need to describe how to correct those. So it's sort of pushing the problem down the road. So one idea is to now try to use the core to correct the proof. They may seem very counterintuitive because the proofs were made to help correct the core. How could the core help with the proofs? And it's non-trivial. We need to introduce some more properties of our proofs in order to make this happen. So one thing we'll insist on is canonicity. So a PCP of proximity is canonical if for any valid input in the language, there's a unique canonical proof P of X that's always accepted. And if you're provided with an input proof pair that is far from any valid input proof pair, then it is rejected with high probability. So the simplified intuition that we want for this talk is that if you're provided a proof pi that's very far from the canonical proof P of X, then even if X is in the language, you should reject X and pi with high probability. This is in addition to rejecting inputs X that are not in the language with high probability. Okay, so let's see how this intuition helps us with our problem. So let's say Snoopy is presented with this composed code word where the core is uncorrupted and this proof string is almost entirely corrupted. What's going to happen? Well, Snoopy can just run the core corrector with I star as the index and R star as the randomness. And that uses this proof, pi I star R star. But when he tries to use this proof with the PCP of proximity, because we insisted on canonicity, this proof is very far from canonical, since the input is uncorrupted and the proof is very corrupted. So due to the canonicity, we'll reject with high probability. Okay, but what if now the input is also very corrupted? So now you could have it that the proof is corrupted in such a way that it becomes the new canonical proof for this corrupted input. So maybe canonicity is not really going to help us out. But in this case, we use the observation that if there are many corruptions among what Snoopy samples, if he samples a random coordinate, with high probability it's corrupt. So it reduces the problem to detecting a corruption in the core. And we know how to detect a corruption in the core. You run the core corrector. So this is the rough outline of how our composition theorem works. So just to recall, we needed these PCPs with canonical soundness and self-correctability, and this was enough to let us correct the proof strings. In the paper, we construct two PCPs of proximity that satisfy these properties. One is reminiscent of the BFLS PCP construction, and one is reminiscent of the classical Hadamard PCP construction. And both these PCPs are used in the original proof of the PCP theorem to construct a constant query polynomial size PCP. And the way we use them is pretty similar. So we follow the proof of this PCP theorem. We start with a locally correctable code that has very large query complexity, polylogarithmic. We compose it with a BFLS PCP to reduce the query complexity to something sublogarithmic. And then finally, we compose with the Hadamard PCPP to get a constant query relaxed locally correctable code. Okay, open questions. So one is to reduce this roughly k to the 4 blowup that we get. And so the current barrier for our construction is that we have these two compositions that I described on the previous slide, and each of them appends roughly n squared proofs, where n is the input relaxed locally correctable code length. So even if you start with something that has size roughly k, you're going to k squared, then k to the 4. Another open question is to construct relaxed locally decodable codes. So not correctable, but decodable, like what Ben-Sasson et al. Did, with very small block length. And if you can construct these with small enough block length, then you'll be able to appeal to lower bounds for locally decodable codes and separate locally decodable codes and relaxed locally decodable codes formally. Okay, thanks.
Time for a couple of questions, maybe while the next speaker steps up.
So I wasn't sure if I understood correctly the distinction between canonicity and just local flexibility on the product space of the proof and core. So isn't it just like a reformulation of local flexibility on
It is some sort of like property testing of are you close to a valid input and its corresponding canonical proof. And the verifier should reject with probability proportional to the distance from what it's given to a valid input end.
if you approach, for example, a linear rate, right, you get for example, a locally flexible code with linear rate that you know is out of reach is now.
Sorry, I don't follow.
If you would decrease the dependency of k, right, something would be like O of k. Something would be very, very close to linear rate, you would get something which is locally tested with a constant rate.
So are you saying if you get an extremely efficient PCP proximity, then you would get...
That's why the fact that canonicity is kind of another way for local stability.
Possibly. I'm happy to discuss it further offline. Yeah. Okay. Yeah.
So this notion of relaxation for like LDCs and LCCs, does it imply anything like, you know, when I get the I don't know symbol, can't you just choose another set of queries, you know, coordinates to query from your distribution on query, and then, you know, get like a Las Vegas algorithm or something for recovering it? I'm just trying to wrap my head around
Yeah, this requires some assumptions on the distribution of queries that the corrector or decoder is making.
Right.
For the relaxed notion, you can get some properties like the distribution over all coordinates of the coordinates that are queried when trying to correct that coordinate is uniform, but for any individual coordinate, it may be that no matter what I try, I could just keep getting bought if the
I see, so
if the
it
things
doesn't
are.
imply anything like that you can sort of repeat.
Yeah. not necessarily. You would need some more assumptions on the query structure.
Thanks again.